Okay, so welcome everyone. So maybe we can start now. Okay, so far we have seen LSH for Euclidean distance and angular similarity, real valued vectors and Euclidean distance, and real valued vector for angular similarity or cosine similarity. So we'll see one more LSH where search for sets and Jacquard similarity. So I hope I'm audible and you can see my screen.
Yes, sir.
Okay. So here our input is sets and similarity measure is Jacquard similarity. And suppose we have, say, two sets A and B. So their Jacquard similarity is basically
A intersection B by A union B.
right, intersection by A union B. Right, and basically the ratio of size of intersection versus union. And we can also, so suppose say maybe this is set A, this is set B. These are common element. This is so here the Jacquard similarity will be how much? Ratio is intersection 3.
3 by 6.
3 by
1, 2, sorry.
9.
Yeah.
Okay. And sets can also be represented as binary vectors, right? So for just sake of convenience, we'll view sets as binary vectors, and then we'll see an LSH for the sets and Jacquard similarity. Sets can so be as binary vectors. So suppose our universe is say maybe like this. So this is our universe, and the sets that we are considering are subset of this universe, right? So for example, say our first set, say S1 is A, B, and D, and S2 is say E, C, and D. Right. So what is their Jacquard similarity of S1 and S2 is intersection is 1 by 5, right? So now we can also view this as binary vector. So So basically for right, so basically we can design a vector of size of the universe, right? So we consider vector of size same as the size of universe. Okay. And now basically how to represent this set S1 as ABD. So we'll just put the, sorry.
So why you have considered F again? F is, acha, sorry, it's in X. Okay, sorry.
Yeah, so this is, so basically so here our aim is to represent set as binary vector. So first we'll see what is the size of, what should be the size of binary vector. So size of the binary vector is size of the universe, and each position is assigned to maybe one element of the universe, right? So here our in universe we have say A B C D E F. So we generate a six-dimensional vector, and each feature is assigned to A B C D E F respectively, right? Now the thing is how we represent this set S1. So we'll just see A B D are present. So we'll just put A
One
D
one zero
and
1 0
remaining
1.
as 0, right? Similarly for ECD, we'll just put E C D as 1 and remaining as 0, right? And here the Jaccard similarity will calculate. So suppose I'm noting this as say S1O and S2O, their binary representation, although they are equivalent. So what will be the Jaccard similarity here?
Numerator is 1 for sure. No, sorry, it is last also. So 2, 0 0 1 1. DNF is matching. I don't know.
2 by 5, sir.
No, it should be 1 by 5. Like,
But zeros are also matching. So are we taking only cases where ones are matching?
1 is matching, right?
Okay, then say 1 by 5.
Yeah. So basically, and how we can represent this as binary operation?
And case.
Yes, and right. So we'll right. So basically, the number of ones in S1O, S2O, right? So this is 1. And what should be in denominator?
Anything other than zeros. Both
Yes.
zeros.
Yes. So how we can represent this using any binary operator?
Or
Or, right. Number of ones in S1O, S2O, which is basically 1, 2, 3, 4, 5. This is 5. So basically the idea is we can represent set as binary vector also equivalently. Okay.
so why that S1 O, why are we representing it as O?
Basically just the representation in binary vectors. So this is just a notation, nothing special about it.
Okay. I confused it for zeros. Okay, thank you, sir.
Okay, so now we'll see kind of a LSH algorithm for sets or binary vector that approximates Jaccard similarity, right? So our input is set or binary vector, and similarity measure is Jaccard similarity. Right, and again this is have you seen this algorithm, Minwise independent permutation or MinHash in your data mining course?
No, sir.
Okay, so the algorithm name is Minwise independent permutations, and this is due to Broader, Charikar is freeze, and Mitzenmaker. I think it appeared in Stock, which is very like reputed conference in theoretical computer science. And basically this algorithm is also used quite a lot in practice. Okay. So first we'll see the algorithm and we'll try to understand the algorithm via one example. Okay, so let's see if it works. Okay, so okay, so suppose these S1, S2, S3, and S4 are our input. So suppose we have say some universe U, and we have S1, S2, S3, and S4 are subset of that universe, right? And for simplicity, we assume that these sets are represented as binary vectors like this. Okay, so suppose your S1 is, for example, say 1 1 double 0 triple 0 1 1, and this is 0 0. Okay, so suppose this is our input, and this is, I think, just if I delete it, it will, everything will go. No, it's fine. Right, so this is our input. So any doubt? And so you can think of, there are 4 points in our data set. Okay, and we'll generate basically okay. So these are our say S1, S2, S3, S4 are our sets that we represent using binary vectors. And our hash function is basically in order to calculate our hash function, we require permutation, right? So permutation in D dimension. So suppose size of universe is D. So we generate a D dimensional permutation. So basically it's just a random rearrangement of number from 1 to D. That's all, right? So suppose we, for example, say we are generating 3 permutations. So for example, we'll go them one by one and we'll see how we use this permutation to hash our input elements, right? So suppose our first permutation is 2, 3, 7, 6, 1, 5, and 4. So basically, this is a permutation in 7 dimension, which is just random rearrangement of numbers from 1 to 7, so that everyone is present. Right. So is this point clear? Yes or no? You can say if you understood
Yes,
this.
sir.
Okay. So now using this permutation, we'll calculate the hash value of S1, S2, S3, and S4. Right. So and the process is basically we'll look the index of the permutation in which corresponding to 1 in our input points, right? So suppose our input is at this, for say S1, we have 1 at so this position, this position, this position, and this position. And for corresponding to these positions, the permutation index is 5, 4, 2, and 3, right? So we'll see what is the minimum of 2, 3, 4, and 5. So the minimum is
2.
2. So this is corresponding to pi 1, this is pi 2, this is pi 3. So minimum is 2. So 2 will put over here. So basically, we are generating a kind of signature matrix where we are storing say very kind of compact representation of these our input point. So say S1 prime correspond to compact representation of S1 is using this hash function, say pi1, right? So we put 2 over here. Similarly for say S2, so we need to see in which index we get 1. So we have say 7, 6, and 1. Right? So for S2, we'll focus on the index of the permutation which corresponding to one position in S2. So we have 7, 6, and 1. And what is the minimum?
1.
1. So this will be 1 over here. Right. Similarly, for say S3, we need to focus on say first and last two. 2, 5, and 4. Minimum is 2. Put it over here. Similarly for S4, like 3, 7, 6, and 1.
1.
1. Okay. So now we generate. So we just repeat it using different independent permutation. Right. So suppose we take another permutation as say 4, 2, 1, 3, 6, 7, 5. So here again we need to fill this row, right? So what do we need to put over here? Can you just tell me? For this position, basically we need to see the value of S1 using pi2.
It is 2.
2. Why 2? Because
The second is 4275. The minimum is 2.
right. And similarly for this, for S2,
1.
1. For S3,
4.
4. For S4,
1.
1. Right. Suppose we take another permutation, say 3, 4, 7, 2, 6, 1, 5. So again, what will be the values?
1.
1,
2.
2, right?
1, 2.
1, 2. Very good. Okay. Now basically using this signature matrix, we'll try to approximate the pairwise Jaccard similarity corresponding to input point, right? So what is Jaccard similarity of say S1 and S2 in the original? Like, and what is our estimated Jaccard similarity?
Originally is 0.
0. S for S1
Originally,
S2. Correct.
right. And estimated will be basically we'll see the number of places where this values, hash values are getting matched.
0.
And we scale it by the number of times we are repeating, right? So none of them are matching. Like 2 is not matching with 1, 2 is not matching with 1 is not matching with 2, so it will be 0. Okay. So now let's see Jaccard similarity of S1 and S3, and what is
3 by 3 by 4.
right? So it's 3 by 4, and what is estimated Jaccard similarity of say, from S1 and S3 prime?
2 by 3.
2 by 3, right? So basically you can see that they are kind of roughly approximating this original Jaccard similarity, right? Okay, so right, so I hope the with this example, this hashing step is clear, right? So our hashing algorithm is we take a permutation pi from D to D. Basically, we generate a random permutation. And we calculate, and suppose this is, we're denoting our hash function like this, h pi of u, where u is some input set. So we permute this set u using this permutation pi and calculate the minimum. So basically it's just summarizing the step that we did using in this example, right? So now okay, so our theorem is, so suppose we take, so this you can think of, this is our H pi1 S1. This for no, sorry. This is for yeah. This is for H pi1 S1, right? Similarly, this is for H pi3 S4, right? So basically, we are just filling these entries, right? So is this point clear to everyone?
Yes, sir.
Okay. So now, can you tell me the following? So suppose if we take two sets, say U and V, right? And if we take a random permutation and calculate their corresponding this minimum value, and this is called MinHash. That's what we call this MinHash, right? And we calculate their MinHash value. So what is the probability that their hash value will be same, right? So is my question clear to you? Like we take say two sets U and V, two sets of binary vector, and we take a permutation and we calculate the corresponding MinHash value. What is the probability that their hash value will be same?
It's equal to the probability that their actual values are same. And
Okay. Okay. So suppose we just try to understand this with example. So suppose we focus on say S1 and S2, right? And if we are taking say random permutation, say pi1, and we are calculating their corresponding MinHash value. So is there any chance like no matter like if we suppose and choose another permutation, say pi4. So far in these three examples, these values are different. If we take another random permutation, say pi4, is there any chance that their corresponding value will match?
so it's the hash will be same if the minimum of pi is in the locations where there are ones, right? So
Yes,
how do
yes.
you mathematically say that?
Yeah, so this is what we have written like this in this algorithm, right? So basically, yeah. So what is the chance that if we take another random permutation and the MinHash value of S1 and S2 will be same? Is there any chance or not? There is no chance, right? Because there is nothing common in S1 and S2, right? You can try generating some more example
Yeah,
of
yeah.
permutation and convince yourself that for S1 and S2, it is kind of unlikely, right? Okay, what about S1 and S3? So, so suppose what about S1 and S3? So what are the chances that uh, if we permute the index of S1 and S3 with one random permutation, their corresponding minimum value will be same?
Okay, then it will
So
be
it can,
3 by 4. I'm just
yeah.
guessing. Max will
Yes.
be 3 by 4.
So
So
essentially,
if in
the
those 3 by 4 locations,
Hmm.
if we get them, if we put a minimum, so we have 7, and in those 3 locations, what is the probability that we put a minimum?
Yeah, so basically, if we are calculating the probability, so the using the standard thing, like what are the favorable cases? So favorable
Three
cases will be
cases.
like the place number of position where the one is getting matched. right? So which is
Okay, so
which
you're
is
saying
what?
the
3 out of 7, right?
Yes. So in this example, it is 3. In general, what it could be. So this is for S1 and S3. In general, what it could be, like size of intersection, right?
Yeah.
So it is. So this is favorable case is size of intersection between U and V. And what are the total possibilities?
NC size of intersection.
Huh? Sorry?
NC size of intersection.
Or union of U and V?
Union of U and V. Right? Union of U and V captures all the possibilities.
So this is nothing but again comes boiled down to jackets, right?
Yes, right. Yes, you're right. Union V. So this is Jacquard similarity of U and V. Right. So the probability that their hash value of two data point is same. So the favorable cases are what? Favorable cases are like the number of positions where one is getting matched in both U and V, which is nothing but size of intersection of U and V. And the total possibilities are like the size of union, which is nothing but JS of U and V. Right. So this gives LSH for uh, Jacquard similarity. Right. So is it easy to see that this is LSH for Jacquard similarity?
Sir, are we doing this for 1 pi or all?
So this is for 1 pi. So this is, but again, we can put this in this framework. This framework. Right?
So one bucket here would be a combination of pi 1, pi 2, pi k.
Yes. H pi 1, H pi 2, H pi k.
Okay. And
Right. So again, like, so this guarantee is roughly the guarantee that we are getting using MinHash is roughly similar to this. Like the probability is that probability that hash value of two data point is probability that hash value of two data point is same is equal to their similarity. Right? Or in case in here it's angular distance. So roughly the same guarantee we are getting over here. Right? Again, we can calculate P1 and P2, and we can calculate rho, which will come out as 1 by C. So is it easy to see this? Or right? So exactly the same calculation will follow what we did in case of cosine similarity, right? So here probability that h of u is equal to h of v is Jacquard similarity between u and v, and if Jacquard similarity between u and v is smaller than say some parameter s, so probability that uh, Jacquard like this will be at least 1 minus j. Similarly, like here it will be 1 minus c into j, and again the same calculation will follow. Is it easy to see, or should we quickly do it just for sake of completeness? Okay, so anyway,
before that, one question, can you scroll up a little near the pi 1 by 2 by 3? Here, so the probability that we've written is for 1 pi.
Yes.
Which, for example, which h pi 1 is 1, if we take it is 2, and that is the actual value, but we are saying that the probability is equal to the similarity of S1 and S2 in this case.
Yes, yes, yes.
Okay. Okay, yeah, thank you.
Okay. Okay, so anyway, just for sake of completeness, we'll just quickly do it. So our similarity estimate, so suppose we denote it as say S. So that is, so first we'll just calculate expected value and variance of our estimate, and then we'll see the parameter corresponding to LSH. So our similarity estimate is an indicator random variable of h pi is equal to h pi v, right? And similar to what we did in case of MinHash, expected value of S is probability that h pi u is equal to h pi v, which is js of u and v. So suppose we denote it as by j. And what will be the variance of S? Will be E of S square minus E of S whole square. E of S square is what? That will be E of S only, because S is indicator random variable. So it takes value 1 when h pi u is equal to h pi v and 0 otherwise. It is expected value of S minus expected value of S whole square. So this is j minus j square. So this is j 1 minus j. Right. And suppose if we are repeating it say k times, so here we are repeating it 3 times. Suppose in general we are repeating it say k times. So our new estimator will be average of all those estimators. Right. So this is sigma si by k. And again, you can show that by linearity of expectation, E of S is say j, and variance of S you can calculate. So that will turn out to be j into 1 minus j by k. Right. So this is regarding the expected value and variance of the estimate. Now, when we see this as LSH, what are the how to choose P1 and P2 and what will be the row value, right? So again, if say Jacquard similarity between say two data point P and Q is more than S, then maybe I should take J. Then probability that HP is equal to HQ, where P and Q are subset of universe. And if so this we can take as P1 and this we can take as P2. And again, like rho will be if we calculate log P1 by log P2, this will turn out to be 1 by C. Right. So again, we'll get the same guarantee, roughly the same guarantee that we get in case of SimHash. Right. So we can put this MinHash in the framework of LSH, and we can solve approximate near neighbor problem for sets and Jaccard similarity. Right. So is this point clear? You can say yes or no at least. Like if it is clear, then say yes, or if it is not, let me know your doubt.
Yes, sir.
Okay, so now we'll see some quick applications of LSH. So yeah, so far we have covered LSH for, we have seen LSH for real valued vector, then cosine similarity, we have seen LSH for real valued vector and Euclidean distance. We have seen LSH for sets or binary vector for Jaccard similarity. But there are several other LSH knowns depending on different data type and similarity measures that we have not covered. So for example, real valued vector and for inner product. But that can be computed by doing some pre-processing in the input, and we can use LSH for cosine or Jaccard similarity, cosine and Euclidean distance. LSH for say binary vector and say inner product. That can be computed via basically doing some pre-processing in the input and using the LSH for Jaccard similarity. We can, it's known that LSH for Jaccard similarity, after doing some pre-processing in the input, can be used as LSH for inner product for binary vector. Suppose say binary vector and for Hamming distance. So this is also known, like here the idea is hash function is just sampling a random bit from the input, right? And can be shown that that works as LSH for binary vector and Hamming distance. And again, real valued vectors for LP distance. That is basically doing some modification in the LSH for Euclidean distance. Real valued vector for LP distance, LSH for real valued vector and LP distance is known. Similarly, like there are some more LSH known for different data type and similarity measures. But these, the thing that I have covered so far are kind of most basic and the fundamental. Okay, so now we'll see some quick applications of LSH. So have you seen or studied any application of LSH in the work you do, or like?
So we heard of this used in anomaly detection,
Okay.
like local outlier factor,
Okay.
locality sensitive hashing, those kind of things, but not beyond that.
Okay.
I mean, means we recently studied one paper in DM where we use this for first story detection in Twitter.
For detecting what?
In Twitter, I mean, there are a lot of tweets. You need to, have like first one, like there will be multiple with the same stories, but you need to
Okay.
find the So one, the first tweet.
Okay. Yeah, so in all those applications, it can be used potentially. So basically, basically the idea is first, given a problem statement, first try to find out how we can represent the data. So for example, if suppose the data is a text, so how we can first represent it using some mathematical object like
Vectors.
vectors, using different embedding scheme like sentence to wake, doc to wake, and so on. And then we need to focus on what is the underlying similarity measures, which captures the semantic similarity of the original data object. Right. So first thing is to find how to embed or represent the data using some mathematical object. Then basically, what is the underlying similarity measure that is capturing the semantic similarity, right? That is capturing the semantic similarity. So once we are done with this, then we need to identify which is the LSH. Which LSH should we use? By LSH for the data type and similarity measure. Right? And then basically we pre-process the data using this LSH, right? Using this bucketing approach. So this is okay, and we just repeat it 12 times. Right, so this is, we can call it as scale bucketing. And now, for example, in your application, so first we have pre-processed, first in, say, in your application, you can first represent the data using, you represent the tweet using, say, doc to wake or sentence to wake. And then, and the cosine similarity will be the similarity measures, that is capturing if the cosine similarity is large, then the basically the underlying text similarity is large. And then we basically use, in that application, we can use MinHash. And the tweets that we have seen so far, we can just arrange them in hash table like this. And once we get in a new kind of new tweet, first we represent it mathematically using the embedding algorithm that we, and then we calculate the corresponding hash values, and we'll see in which bucket it falls, and from there we find it the closest one. Right. So typically this is the kind of high level approach in which LSH can be used. Right. And this has a so this is could be used in, so maybe whatever application you are telling, or it can also be used in, say, faster deduplication. or maybe finding similar pairs, right? So in these, basically, like we need to first arrange this scale bucketing of the data points. And if we have to do faster deduplication, so basically we'll go in each bucket and we'll see what all points are falling over there. And then basically we calculate the ground truth similarity, and based on that we can prune the duplicates. Similarly, we can use it to calculate the similar pairs. So again, we'll calculate this scale bucketing hash table, and in each bucket we'll see which points are getting mapped, and we'll calculate the pairwise distance, and from there we can prune the similar points. And again, the advantage will be, suppose if we have, say, n points, and so if we have to calculate the original the similar pairs in the n points, so we need to calculate all these n choose 2 pairs, which can be very large if, say, your n is of order, say, millions or billions. If it is n is of order millions or billions, right? But using this KL bucketing scheme, so there are not very large number of points mapped into each bucket. So this can be sufficiently pulled down to something very smaller. Right. So this is just kind of high level framework which can be used in different application of this type. Any other application that you could think of?
So these hash buckets are similar to clustering, right? Clusters, right? Can we draw similarity
Yes.
and there?
Yes.
And in, let's say, online cases for clustering, let's say, we are not defining the number of clusters here, since you mentioned that if a new bucket is needed, it can be added on the fly.
Yes.
So in those cases, this can be helpful, right?
Yes. Yeah, in a way, like you are right. So this bucket is nothing but cluster of data points which are similar to each other. Right. And in a way, like, so in fact, LSH is used to accelerate clustering algorithms as well. Right. So suppose when you apply k-means, what you do, we first sample, say, some k points, and then calculate the distance of all the points with those k centers, right? So if your, say, number of data points is very large, right? So you need to calculate the distance of all the points with every center, all the points with all the k centers, which could be very prohibitive, like expensive when, say, n is very large. So there, like, people use this LSH techniques so that for to compute the similar points of the cluster centers that we have calculated, we don't need to go over all the endpoints, so that we can accelerate the k-means clustering. So this is one known result. I am not able to recall the paper, but it is this LSH has been used in accelerating clustering algorithms as well.
Sure, sir. So, if you find that paper, please share with us.
Sure. And any other application can you think of?
Like matching customer records.
Yes.
Fingerprints detection also can be used.
Yes, fingerprint detection, right. Again, basically, so this can be put in this framework. So suppose we need to first find out how we represent fingerprints in some mathematical objects like vector. Then again, we need to focus on what is the similarity measures which captures the similarity, like what is the similarity measure that we need to use, so that if the vectors are similar, then the underlying fingerprints that are represented by those vectors are semantically similar. And once we are identified like similarity measures, then we can use the corresponding LSH algorithm, and again we can use this bucketing scheme.
But in case of fingerprinting, everyone will have a different fingerprints, right?
Yes.
So how it is going to help us?
No. So suppose the application where where we do this biometric attendance. Right? So there are some set of employee which works for some organization, and so their fingerprints are saved. So suppose if say some new person want to come in, then basically it can be quickly verified whether that person belongs to the existing set of employee of that organization or not. So there it can be used, right? So you just collect the fingerprints of all your employee, generate the scale bucketing scheme, and install this software in the fingerprint detection machine, right? And once
Also,
This
sir,
Yeah.
in case of partial fingerprints, if only partial fingerprints are available,
Yes,
there we can do matching, right?
yes. And this partial versus exact can be taken care of choosing the appropriate value of C, basically the error that you willing to afford, right? So essentially, it can be used in application where first the number of data point is large, and basically our aim is to quickly compute, say, some similarity.
I think LSH, all the applications are with respect to the same constraint, right? Like your data volume should be large and
Data volume
you
is,
need.
should be large,
I
right?
mean,
Otherwise,
if the data volume is lesser, then we can go for the traditional approach itself. We will
yes,
not
then
go
you
to-
can do the brute force, right?
Yeah. So I have two questions. So like as you said, like the real value vector with couple of things we have done, like cosine similarity, the Jaccard similarity. Then we have seen Euclidean distance. So when we are targeting a problem, like which one we should choose, and is it a trial and error basis, or is like something like a application specific? Like we can come to know upfront that okay, if this kind of problem is there, then Euclidean distance would make sense more than Jaccard similarity. Like how to approach that similarity?
So that is basically another problem. So for that, domain knowledge and some other thing will be required. So that is basically the first part of the problem: how to represent the data mathematically, and what is the similarity measure that we need to choose, which captures the underlying semantic similarity.
Yeah,
Right?
and how to do it mathematically also, I am not understanding for like in case of like this fingerprint or like the Twitter fast story detection example, like this kind of thing, like how uh, we will derive, like I understand like we will form a vector, but how to exactly convert that stream of sentences to a vector, and which would help us in the determining the similarity measure, that I'm not able to analyze.
So for that, like different representation algorithm, like this doc to vec or sentence to vec, these kind of thing can be used. And maybe like this. So basically there are different representation algorithms. So that can be used by like
Basically, the TF-IDF.
a TF-IDF is one way of to represent text into vector. And autoencoder, like there are a number of ways. So for that, some domain knowledge and some other thing would be required. So but our The job of LSH starts once we have identified this first and second step. Right?
Yeah, but if we are not doing the first and second step properly,
Yes.
then maybe it will impact the performance of LSH.
So basically,
not performance, maybe the accuracy.
No, in order to apply LSH, you need to have first and two step with you. Right?
Yeah.
Otherwise, you cannot apply LSH. You cannot apply LSH directly by passing, say, some text to some hash function. Right? You first need to represent it to either vector or sets or any other mathematical object, and then use the corresponding similarity, corresponding LSH function.
Yes.
Okay, so that's what I planned for today. Any other thing that would like to discuss now?